few minutes and review where we're at. First though, it wasn't long ago, I recall, I saw a Dick Tracy watch for sale. Now, when I mentioned this to a student, the student said, "Neat, a watch that has a radio and a TV built in." Now, this student had obviously seen the Dick Tracy cartoons, and if you ever have seen the cartoon Dick Tracy, he has a watch and he talks into it and he has a two-way TV and so forth. And that is, of course, what the cartoon character wore. Of course, that's not what I'd seen. All I saw was a watch with a picture of Dick Tracy on it, just like a Mickey Mouse or a Pluto or other watch. Well, technology is often like this. One has to understand the user's expectations to know if what you're making is really useful and really welcome. If I went out and announced to the world, "I've invented the Dick Tracy watch, come and buy it," there would be a lot of confusion unless people all agreed or understood what it is. And so it is with all sorts of technical achievements we see today and we hear about all the time. Well, we've been looking at the history a bit, talking mainly about what are the big trends and activities and ways of doing things. And by the time we get to the Middle Ages, 1400s, 1600s, 14s, 1200s, much of the engineering environment that we see has taken shape. Subsequent to this time, what really continues to happen is that manpower continues to increase in cost. Because as we move from these ancient Roman days and heavy slavery into the Middle Ages, at first we have serfs and slaves tied to the land, and the value goes up a bit with the land values, and gradually people get freedom, and there's craftsmen, and they demand wages, and gradually their value goes up and up and up. And so labor goes up in value, which means there are more consumers who we have to make happy, and which also means that it's more expensive to do things. And that creates this driving force that tends to happen. In addition, at the same time this is happening, machine tools are getting more and more sophisticated. As we talked about, there's a structure. One thing leads to another, so you don't have to rethink your problems all the time. And this is particularly true when you come to equipment and come to all sorts of embedded devices. Once we have electricity, and we've defined electricity as 110, we don't have to worry the next time we design a machine what's in the socket. Is it 110 or 150 or 160? It's 110 or it's 220. And so we just take there and we use that and we build forward. And the fact that we get these structures and we can build forward allow us to get more and more and more sophisticated. It is also true, generally speaking, once I've made a tool, I can use that tool to make a better tool. I can then use that tool to make a better tool. And as I keep improving my tools, I can continue to move everything forward by getting more and more sophisticated. So that is the other thing that happens then, is we continue to improve our tools and build our structure forward. The other thing, of course, is our knowledge base expands. In much of the Middle Ages, the main repository of knowledge, of course, are the monasteries, and out of these gradually goes colleges and universities. But as we move beyond this, wealth starts to move in, people start to get independence, more and more knowledge starts to accumulate. And the knowledge grows, and of course as the knowledge grows, we're able to solve more problems in a better fashion. Now, the energy, of course, moves into alternate forms. Many of the forms we're still working with today, the dominant form, of course, industrially, is electricity. And where do we get electricity from? Well, of course, in the early days, largely coal and steam. These days, wind turbines, we're trying to move beyond. Solar energy, we're trying to move out and beyond as we move. But we're looking for alternate energy because the cost of manpower as a source of energy, it's just too high. And so we generate our electricity, we transmit it, we use it. It supplants so much of everything else. Well, The increase in sophisticated industrial tools, our increase in the structure and ability to make better and better tools, leads us to more and more demands on education. And this, of course, is another big thing that pushes technology. In the start of the Middle Ages, especially with the Reformation, there is more and more an emphasis on everyone should read and write. This is the first thing that starts. Broad-based education. Initially, this is pushed because under the Reformation, we want everyone to read the Bible in the Western world. But it becomes more widespread than that and more of a force than that, of course, and we spread education universally. More education, more educated people, more sophisticated use of things, better understanding. And so our education gradually improves, we get more rigorous demand, and that helps us move forward. In addition, engineering and technology becomes more and more decentralized. This is a result of the fact in the early days you only had the king to sponsor, and so they in a sense were in charge of what got done. Later on we had smaller kingdoms, we had ruling groups, we had the Roman emperor and the regional governors and other people, and so you can see that the sponsorship and the power and the money was starting to spread more widely to solve technical problems, which meant there were more problems being attacked. And as we move forward and wealth spreads out, we get more wealthy tradesmen and other groups, engineering becomes more and more decentralized. There's more and more activity and more people are demanding to solve problems. This means, among other things, there's an increase in the ability of inventors and engineers to pursue their own ideas. And we see a lot of new industries and inventions come about because people start to have ideas that they go out and sell, and they raise money. And we see the rise then of individual pools of money, entrepreneurship, if you will, which becomes a big force in the world. The increase in the knowledge base, well, that means we need more and more and more education and more learning. And that means we also need more of an ongoing demand for education. So it's not enough to just learn a little and stop. You have to continue onward. And of course, in the early days, people could go out and invent and do things just by a short apprenticeship. As time goes on and things get more sophisticated, they need at least to learn to read and write, some high school, and pretty soon they need some college to really do sophisticated work. This also means, of course, there's more knowledge. You need to know more. People do have only a certain ability they can absorb, and so what happens is we split technology into more and more specialties. Currently, there are over 60 specialties in engineering and technology, and of course there's overlap, and of course these groups often, specialties work on similar or the same problems or different aspects, but it gives you a sense of how broad the knowledge base becomes and how much a person needs to know that gradually we split more and more. After all, as late as the 1300s, it was not uncommon for people to still write an encyclopedia of the world's knowledge. And so we wind up with specialties in electrical, mechanical engineering, civil engineering, chemical engineering, and so forth and so on. The title of engineer becomes more and more widespread. And this means one, again, it continues to be one who creates, and it's firmly rooted in society. So society, when they hear of an engineer, it means to them someone of ability, someone that you can trust, someone you can respect. This allows technical personnel, an engineer, to be in charge, solve things, raise funding, and direct resources. It becomes quite important. Here, for example, is a Gallup poll that was taken, where they went out and they asked the general population, who in the world do you respect the most? And they responded among a choice of 30 professions who they respected the most. You notice 30% said they trusted and respected engineers the most. This is even more than ministers, who only got 20%, or doctors, and so forth. Lawyers, no one seemed to trust them. The upshot of this is that in our society today, we trust the people who do technology. We trust the technology more than we trust many other groups. And so we give the people and the technology, the money and the freedom to go and pursue solutions and make things happen. Very important. If we did not trust, we would put all sorts of rules and regulations. We would stop innovation and we'd make things come to a halt. But because we believe and trust, our technology moves ahead faster and faster. This is one of the key forces or key philosophies a society needs to be successful. Educational, if we look back at the structure, how did we come along educationally? We go back to Mesopotamia. If you remember, the informal and some lessons that you studied for a few years. We moved to Egyptian, we saw some lesson plans, some report cards. When you went to the early Greeks, it was clear there were more apprenticeships, more writing. When we got to the late Greeks and the Hellenists, now we have lectures. The term lecture, the Library at Alexandria. The Romans certify, and you become a royal engineer. And finally, the French codify into a system that we use today. It's done at the École Polytechnique, 1794. The French codify education for technical personnel. And basically what they say is, well, the first 2 years, you'll learn general information and basic sciences, mathematics, physics, chemistry, whatever basic sciences might be relevant to what you're going to do. The last 2 years you mainly study whatever it is. So if you're an electrical engineer, you study electronics. If you're a mechanical engineer, you study machines and mechanisms and so forth. And that is their general system. And then at the end, there's some examinations that you pass and you're certified as an engineer. This is the French system. This is, in fact, what we tend to do today. Today is largely enforced in the U.S. by an agency we call ABET, which is, by the way, one of the few things that accredits worldwide, internationally, is ABET. Engineering and technology we recognize as important enough. It has its own accreditation, own monitoring, and it's global in impact, which makes it unusual. The scientific basis for engineering technology, well, in the Mesopotamians we start with basic mathematics and algebra. This moves forward into the Greeks, which start to add more mechanical, write some texts. We see pneumatics develop and other sorts of ideas in the Greeks with the textbooks. When we get to the Hellenists, now we have heavy instructional. They have regular texts, massive texts you study. They get some standardized texts, ongoing literature, ongoing lectures. You write treatises to continue to develop it. You give demonstrations and models. And so the scientific expands and expands as we move on and lays a good solid structure. There's a legal environment that develops. The legal starts back with Hammurabi, and we saw much of their code is dedicated to engineering technology. It's an eye for an eye sort of code. You kill somebody by your negligence, we kill you sort of thing. It moves forward, and in the Roman period we see longer contracts, more specification, and compensation. For example, the suing for cost gouging. We pay for things. And this becomes more and more codified as we move forward. And so we have this codified legal environment, contracting environment, liability environment that develops. Along with this then is the contracts. The contracts start, Hammurabi, so many square feet, we pay you so much. When we move forward, the Greeks, couple pages, a little bit more, maybe a brief plan, so much for this. The Romans, 50, 60 pages, and now we also have inspections. And so we write specifications, inspections, certifications. So from then onward, we have detailed specs. The builder may be different than the designer. The certifier may be different than all of them. We may design here and build miles away and not see each other. And we do this with inspections and certifications and contracts. Now, there's other key elements of the legal environment that are added mainly through British common law. By the way, the reason it's called British common law is because in the British Isles, what develops is the Romans have brought their legal code. The Roman Empire falls apart, And later on, the Normans, who are basically Scandinavians who settled in France and intermarried, come and they conquer the British Isles, and they set up a series of courts all around the Isles that are local. Well, to try to keep the laws regular, all these local judges meet once a year and discuss what the rules and laws are, and they come up with things in common, ergo common law. In the U.S., we are largely a British common law modeled after sort of country. And in the common law, you get more ideas of compensation. You also now develop the idea of proprietary information and trade secrets. Very key to technology is the idea that if you have a secret, you have rights to that secret. And for someone to steal it, it may cause them to owe you compensation for your secret. Most of the details in technology are trade secrets, are held as secrets rather than protected other ways. There are other sorts of intellectual property rights that come out of British common law. Patents very strong. In the U.S., we are the only unique country in the world where we have as a fundamental right of a citizen the right to have a patent. Patent laws then are meant to encourage and push inventions by securing economic rights for the inventor. Intellectual law also involves copyrights. You can copyright things. And so that comes out of common law and becomes part of our environment. Planning continues forward. Planning gets more and more symbolic. If you're an electrical engineer, you know hundreds of standard symbols. And every time you see that symbol, no matter where you see it, no one has to tell you what it means. You know what it means. If you're a mechanical, you have similar sets. If you're civil, you have other sets. And so the symbolic becomes very regularized and part of our environment. This, remember, starts back with the Mesopotamians who have simple symbols. The Egyptians a little more. The Greeks get even a little more abstract. By now it's just part of what we do and we learn our symbols. Part of planning then, of course, also is time and resources, and that starts back early on with the Mesopotamians and the Egyptians, although the Egyptians are the masters, and it moves forward and the Romans add in the costs. So then we have time, resource, costs with the Romans, and moving forward, and modeling. The fact you often build a model before you make it. Today it might be a software model. Well, you still build a model first, starting at least with the Egyptians, moving forward, and this becomes our environment. This is what we do then. Is we plan, we model, we do make symbolic drawings. The financial aspect that develops, well, back in Mesopotamia, it's a sponsor. It's whoever the king is. That's who it is. By the time we get in Egypt, it's Pharaoh or a member of the royal court. By the time we get to the Greeks, we start to have contractual and we start to have smaller units. When we get to the Romans, it's cost-based and there's lots of people participating, and so the financial becomes a cost, eventually becomes like it is today. Cost-based, you do this, we pay you that, here's a contract, here's a spec. That's a financial basis. Advancement. This is something that is relatively unique. There are only a few fields where this is as true. Starting from day one, in technology and engineering, it's merit-based. You start with the Egyptians, where we saw someone who is very low rise to number 2 to Pharaoh in the land because he was good at design and technology. Strictly on the merit, you go up and up and up. Here we have rigid class society in Egypt, and yet you can rise if you're good. This continues with the Greeks, and with the Greeks we noted that merit, it becomes clear, merit is several things. It's technical. Can you do the good technology, design, and so forth? It's organizational. Can you organize things to get things done? It's communication. Can I clearly make my ideas move to other sources, write them down, allow them to be implemented? And it's planning and problem solving. It's these 4 things. It still is today. These 4 things. Those 4, if you're good at all 4, you go to the top of the technical profession. If you're good at only one technical, you may go a long ways, but really you need to be all 4, because it takes all 4 to get something done. And in technology and engineering, it's only if something gets done. being a Da Vinci and making beautiful drawings does not get you recognized as an engineer or a technical person, because it doesn't do anything other than make a pretty drawing. Also part of the advancement is you actively go out and recruit the best. This we saw with the Hellenists, where the Ptolemaic line goes out and they recruit the best from all over and sponsors them and pays for things. And this is still true today. We recruit the best because the implication of solving problems well and getting the solutions done and getting them to work well is so huge that we still do that today. We also see that design becomes something as a discipline, is another part of the environment. Design is a discipline in the sense we plan to design things, we lay it out, and we design to our schedule and our plans. This starts with the Hellenists, we see with their Skunk Works, where at Syracuse they set up the first R&D center for military, and it continues forward. And when we got to the Romans, I didn't point it out a lot, but by this time we have specifications, we have costs, we have time constraints, and so we design to a whole list of constraints to schedule. I have designed hundreds of things and run groups that have designed hundreds more of things, and we always do it on time, on schedule, on plan. And people might wonder, how can you do that? You don't know how you're going to solve it, but you do. And that is part of the environment, is you design, build, invent to schedule. Well, many of these items, by the way, have been expanded and further use in the U.S. The U.S. is known as an engineering powerhouse. We're not known as a scientific powerhouse, although we are good at science. We are known as the engineering powerhouse. Education in the U.S. really goes back to Valley Forge, Revolutionary War, 1777, 1778. During the winter months at Valley Forge, George Washington realizes one of the things he desperately needs are some engineers. Now in his time, military engineers, mainly bridges, roads, fording implements, dams, and he desperately needs some engineers to help move his cannons and supplies and so forth and so on. And so he goes to Continental Congress, has some money allocated, hires a Frenchman, and has the first engineering school and graduates the first engineers then at Valley Forge. And they are then in charge of transport, maintenance, fixing and devising different means of armament, and so forth. And they turn to be very successful, very key. The French lieutenant I mentioned is a first instructor. There are 10 commissioned officers who are graduated in the first class, and those 10 are the ones who lead the crossing of the Delaware, who are tasked to put together the transport and get everything across. And after the Revolutionary War, this French officer moves and the school is permanently located at a building near present West Point. And so West Point in the U.S. is an engineering school first and foremost. We all think of it as graduating military officers, and it does. But every military officer graduating from West Point is an engineer, because it's fundamentally first was an engineering school. And so West Point is the U.S.'s first engineering school, and very successful. Now, many of the legal rights of engineers and technology stem from the first Continental Congress in the U.S. And among them, in the Constitution, they established patent rights to promote the useful arts being engineering and design. They also establish and allocate money for engineering societies. Benjamin Franklin insists that we need to form a general union of the useful arts. And so with some money and with a mandate from Continental Congress, they create the Boston Exchange Society. The idea from the start is the U.S. is deadly reliant on European manufacturing technology, and we need to be able to manufacture and develop our own technology here. And so day one, we are going to promote that. Part of the promotion is we give the citizens the right to make money off something they invent. Part of it are these societies and other rights that are included day one. And that's been very successful. Over over the years, there have been other things added. One of the key things are registration laws for engineers. They're called, in the U.S., they're called professional engineers, or PE. PEs are really meant to be civil engineers, having to do with land. Some mechanical engineer, a little bit of electrical. But any engineer can register as a professional engineer, but it's most common really in civil and places where someone certifies something to the public or the government. That's where a PE comes in. PEs, well, they come from the Wyoming land rush. If you remember, in the state of Wyoming, Congress decreed they were going to open it up for settlement, and people lined up along these designated areas. A gun was shot at a certain time of day. People rushed out and staked their claim to land in Wyoming. And the problem that happened was after they staked it, they had to have the boundaries certified as to where they were, and they'd go in town and register. Well, the sort of thing happened that you might expect. A bunch of charlatans moved in, went around, and fraudulently surveyed and gave people the wrong coordinates. So people were going into town and registering the same piece of, 3 or 4 people would register the same piece of land because they're getting bad information, and the charlatans were just taking money for doing nothing. Eventually, state by state, they came up with laws and rules so that only professional engineers could certify things to the government, such as the boundaries of your property, and to register you became a PE, and there was a board. There are now 55 independent boards in the U.S. that do certification. Each state has them, the territories have them, Washington D.C. has one, and generally speaking, if you're certified by Minnesota and you go to Florida, you're not automatically a PE there. You have to recertify in Florida, which usually is not a big problem, but sometimes can be. And so we have added another layer of certification, like something like you might think of the Royal Engineers had. Well, this is the basic environment that has developed and allows us to move forward. Is this legal environment, financial environment, scientific, technical, structure? It's all there. We're moving forward. That's kind of where things are at. We're now able to talk about other things and look a little more broadly about what else is going on. Next time, it will be Unit 12. We'll take a look at another story. In this case, we'll answer the question, which was invented first, the telephone or the fax machine? I think you'll find it interesting. See you later. Bye now.